All right. Welcome, everyone, to the Quantum Sensing for Executives webinar. This is focused on the advantages of quantum LiDAR and PNT devices. We have a special guest from QuantaSense today, and we will learn all about that very shortly. So again, welcome. My name is Dr. Katanya Kuntz. I'm an experimental quantum physicist, and if you're not sure what that is, I have a picture coming up of the type of experiments that I work on. I'm the founder and CEO of Qubo Consulting Corp, where we offer training and consulting on what is this new deep tech called quantum technologies, both for technical and non-technical audiences, because there's a very different language when you're speaking to these different groups. So like I said, this is the type of experiment that I do, or I have done in my life. In this case, I was trying to create this very special beam that you can see here in the middle of the laser table. It's not actually a lightsaber, but it certainly looks like one. It's called a Bessel beam. And so the types of experiments I do, I use lasers and optics and things like that to create what's called quantum states of light. And so this would be technically it's not quantum, but a lot of our experiments look like this with optics, the light beams and things like this. So when I say I do experimental quantum optics, that's the type of work I work on. All right. So again, welcome everyone. We have a few people from the Qubo team on the call helping run today's session with me. We have Lorna, we have Vish, and we have Nathan. So say hello. If you'd like to unmute, you can. Or not.
Hey guys.
Hi, everyone.
See, they're alive. They're alive. So I know Lorna loves to she's going to help with the Q&A today. She has a teaching background. And so I just want to bring her into the floor just for a quick second and say that if you have any questions, she'll be watching the chat. We'll be using Q&A if we have that function today. Things keep changing with Zoom. But put the questions definitely in chat and ask lots because that's the best way to learn. And so Lorna, did you want to say anything else about keeping an open mind and things like that?
Oh yeah, absolutely, guys. As I always say, this session will just be as fun as you make it for yourself, right? And we have experts here in the room. This is your chance to get those one-on-one questions in. So by all means, it is easier for me if you put your questions in the chat. Sometimes it does get lost, or not in the chat, in the Q&A box, excuse me. Sometimes it does get lost in the chat. And yeah, by all means too, if you prefer to raise your hand and unmute your mic to ask your question when the time fits, then that will be great. Also, just a quick reminder, because I am doing attendance at the same time, just to make sure that you do get, I believe, is there a certificate for this, Dr. Katanya?
Yes, there is.
Yes. So you get your cool social media certificate and you get the webinar and all the contact information from our experts here. Please have your name changed to your first and last name. There's a few that I see like initials or just first names. And if you are not a registered person, we might have to have a quick chat behind the rooms just to make sure that we get all the information correct and that you are registered. So that's enough for me. Thank you.
Awesome. Thank you very much, Lorna. All right. So here's an overview of our webinar today, and I promise we will try to keep it to an hour this time. So an introduction to quantum sensing. What is overall this quantum technology I'm talking about? What is a quantum sensor? And applications of these devices. Then I'll go through some examples of quantum PNT devices, for example, quantum magnetometers, and the limitations and the current maturity of this technology. Then I will step through what is quantum radar and LiDAR, and also quantum illumination, if you've ever heard of that. We'll dive down into a quantum rabbit hole, get a little technical, but then we'll pop right back up, and then we'll talk about the limitations and current maturity again of this technology. So I like to give real demo examples. So in this quantum rabbit hole, it'll be the quantum LiDAR demo. I'll show you an actual experiment. And then we will have our guest speaker from QuantaSense. Yeah, he's co-founder and CEO, Abdul Mohamed. And so we'll be hearing from him a little bit later. All right, and so yes, please raise your hand if you like. Type into the chat if you have any questions. I have breaks where I check in with the audience, make sure we didn't lose anyone. But let's get started with a quick intro first. So what is quantum? Quantum refers to quantum physics, also called quantum mechanics, which is the mathematics behind the physics. This is the study of the smallest particles and energy that make up our universe. Things like atoms, ions, photons, those are particles of light. These particles are smaller than what you can see with your eye, even smaller than what you can see with a microscope. So on this tiny, tiny scale, matter and energy and our world just behaves differently compared to our big macro world, the world you see every day with your eyes. But maybe you didn't know, you already have quantum technologies in your life right now. For example, the screen you're looking at could be an LCD or an LED screen. These are quantum devices. So they operate on the principles of quantum physics, but they're not what we call quantum 2.0 technologies, because they're not using individual atoms, particles to do the task. And also other examples like an X-ray. So there's tons of medical exams like MRIs and CAT scans and things like this. Those are all examples of quantum 1.0 technologies, but they're not the next revolution that I'm going to talk about today. And another one that you might be aware of, GPS satellites. So GPS, Google Maps, your ability to navigate around a city on the Earth. And so these are actually using atomic clocks to create a very accurate timing signal. And that timing signal is used to figure out your positioning. And so these atomic clocks are another example of quantum 1.0 technology. So now what's this 2.0 technology, the second quantum revolution? Well, like I said, it's now using these individual quantum objects like atoms, ions, superconducting circuits to do quantum computing, sensing, also communication, encryption, random number generation, things like this, and quantum materials. And so at Qubo, we're helping to bring this awareness to the industry. My background is technical, and also with my communication skills, I hope to shed some light on what are these technologies. And so today, we're going to focus on quantum sensors. So what is a quantum sensor? Quantum sensing is when a measurement is done that has been enhanced. It has a better sensitivity than what we can do with our classical current technology. And this enhancement is due to quantum properties, things like quantum entanglement, which I'll talk about later. There's things like coherence, interference, also using a quantum object, using a photon to do the sensing instead of our typical classical technology. So when you do that, the quantum sensor is leveraging properties of the quantum world, atoms and matter and light, to improve the overall measurement. So you're able to get, to measure these quantities in ways that may not be even possible with our current classical technologies. So what kind of properties am I talking about that we can measure? Well, gravitational fields, magnetic fields, electric fields, single photon detectors, those are versions of quantum sensors. Things like avalanche photodiodes, APDs, also superconducting nanowire single photon detectors. That's a mouthful. SNSPDs. We'll talk about more about those later. So quantum LiDAR can allow you to do hidden object detection, which is very powerful. The timing signals, timing synchronization, clock synchronization. There are so many industries that require precise timing. And so getting a more precise atomic clocks, better, more accurate GPS, things like this. Also other properties like temperature sensing, gas monitoring, and accelerometers, movement. Again, helping with the PNT positioning things. And so what can these quantum sensors do? What are some tangible examples of what I'm talking about? So a quantum sensor, for example, could give more precise positioning in challenging landscapes. So these devices can work in GPS denied environments. Also detecting hidden objects. So there's magnetic sensing and also quantum LiDAR, which I'll talk about more later. And that timing signal. So there's these next generation telecom networks like 6G wireless, and they need more precise timing signals that are beyond what our classical technology can do. And so it's possible that these quantum sensors could provide that. And so this picture here is an example of one of these sensors. This is a quantum sensor that's based off of a superconducting circuit made by Cubic Technologies, a company in Canada. And because it's superconducting, that means it has to be very, very cold to operate, very close to what's called absolute zero. And so it needs to be cryogenically cooled. And so this picture here is a picture of one of the cryogenic fridges that's used to cool down these devices. And so this fridge, also made by a company in Canada, 0 Point Cryogenics. And so these fridges are not just for running sensors, but there's also quantum computing chips that need to be super cooled as well. So there's lots of different platforms, different ways to make these sensors, different, and I'll go through shortly. But some of them require these cryogenically cooled fridges. And so I just wanted to show you, highlight in particular, 2 companies in Canada that is working on this technology. Awesome. All right, let's check in with everybody, make sure no one went to sleep. It's okay if you went to get a coffee, but I hope you came back. I don't see anything in the chat yet. That was just like a basic intro, so I think I'll just keep going. All right, let's keep going. So let's go through some quantum PNT devices. And PNT, again, is positioning, navigation, and timing. So for positioning and navigation, there are tons of applications of these devices. As you see in the middle here, PNT devices. So you're spanning industries from aviation, telecommunications, public safety, agriculture, automotive. All of these industries and more need precise positioning and navigation signals. And so then on the outside here in these light blue bubbles, you see all the classical current technologies that are either being developed or have been developed to create these signals. And so one in particular is the GNSS, right? GPS. And so there's several threats that I'll mention again later. Things like signal blocking, interference, and spoofing and jamming. And so it's interesting to see, yes, there are quantum sensors that are being explored, but like look at how many different versions of classical technologies we use now for these positioning and navigation devices. And so down here, you see atomic clocks. This IMU is inertial measurement units. So things like accelerometers, gyroscopes. And then also gravimeters and magnetometers. So these are all examples of quantum sensing devices that can also play a role in giving us these positioning and navigation signals. And we have come a long way. So this picture here on the right, this is one of the first cesium fountain atomic clocks. This picture is from the 90s, I believe, late 90s. And so you can see it was based off of like atoms. And the atoms are falling. They're actually falling in this like tube thing here. And so that's why it's so huge. And so you have all these optics. Remember my optics table from like that introductory slide? So you got all these optics, fiber optic cables, lasers, and things like that. And then you've got the atoms and things in this tube. So it was a huge device, but it was able to keep very accurate time. And so fast forward to, let's see, I think this was 2010, where we have now this atom-based optical clock, and now it's the size of a quarter. And this clock is so accurate that it would not lose or gain 1 second over 13.8 billion years. So that's how accurate my oven clock loses probably a minute every month. So well, that's pretty incredible, right? And so these atomic clocks, like I said, they've been around for a while. We've had versions of hot atomic clocks since the 1960s. And now they serve as a very fundamental a temporal foundation for PNT architectures. And so what's the motivation then behind looking into quantum sensing? Well, like I said, we know the global navigation satellite systems, GNSS, are vulnerable to things like interference, spoofing, signal degradation, limited resolution. So the accuracy of your position could be only within 10 to 15 meters. There's some applications where that's just not good enough. And so the central role of this GNSS in modern PNT systems means that we have a single point of failure. And so we really want to address that. So there's a real urgent need for a robust alternative solutions for these PNT services. And so quantum sensors could be a potential solution for this because they can operate in GNSS denied or GNSS contested environments because they just fundamentally operate differently to get their timing signals, to get their positioning signals. So they don't depend on like an external source to give them the signal, for example, like linking to a GPS. However, as I said in my overview, I want to discuss the maturity and the limitations of these technologies because, of course, it's not like everything is wonderful and we're all just flying off the shelves finding quantum sensors every day in our lives, right? This is a developing technology, but it deserves its spotlight because it's developing quickly, and it has a lot of power compared to our classical devices. And so this is another example of a quantum sensor. This is a quantum magnetometer made by SP Quantum, also a Canadian company making these devices. And this is a $2 coin in Canada. And so you can see the size, also very compact, very portable. So these quantum sensors have several devices over the classical PNT devices. For example, you can enable absolute, drift-free, and ultra-sensitive measurements. You can measure properties like the inertial forces, gravity, and magnetic fields in challenging environments, like over featureless environments like the ocean. They're very compact usually, so it does depend on the platform, on the device. Some of them can be large and tabletop demonstrations right now, and some of them like this, this is based off of a nitrogen vacancy center, diamond-based magnetometer, and so they're very compact. And also they can have this improved swap and they could be space ready. So SP Quantum is actually partnered with CSA and ESA working on launching these devices into space. Also, the measurements can have long-term stability and like I said before, reduce dependency on external signals for them to operate. All right, so the integration of having both classical and quantum devices working together is probably the best move forward. We're not trying to replace everything classical with quantum because there's still a very strong role for some of these traditional devices. And so it can be complex trying to work with both classical and quantum together. They can have different operational platforms. They have different sensitivity levels. They might have different control requirements, environment requirements. And so it's just to keep that in mind. And so here's some types of quantum sensors that have been used as PNT devices. So cold atom interferometry. So that's where you're making an interferometer. So you're interfering atom beams. You're interfering matter waves, which is just like mind-blowing to me. I can understand interfering light, like how water waves crash into each other, and water waves when they add together in phase, then they make a bigger wave, and if they cancel out, then they make a small wave. That's interference. And so you get that with light. You see light pattern interference all the time around you. through your glasses, through lenses, through optics. So you can do that with atoms. You can interfere atoms, which is just crazy. But you can use these devices to get very, very accurate acceleration measurements, for example, because you're moving your interferometer around, and then your atoms will also react to that movement, and then you'll get a signal that measures how much did you move, and very, very precisely. There's also atomic vapor cells. I'm not gonna, this is a non-technical, so I'm not gonna get too far deep into these. Superconducting quantum interference devices, SQUID. So these two small handheld devices here are examples of these SQUID devices. And then you have room temperature solid state devices like nitrogen vacancy centers in diamond. Room temperature, which means does not require cryogenics to operate. So this device here, Phaser Quantum, is a portable NV diamond magnetometer. So similar to that SP Quantum device I was showing, just a different company. So with quantum magnetometers, it might seem weird that we're using atoms or diamonds or these things to navigate, but think about it. We've been using magnetic fields to navigate for a long time. We use a compass and a map, right? And so having a sensor that's just very, very sensitive to, for example, magnetic anomalies, you can now navigate via those sensors. However, your overall positioning accuracy is still going to depend on the resolution and the reliability that's underlying the magnetic field maps themselves. So if the anomalies aren't on the map, and it doesn't matter if you can measure the anomalies because there's nothing to compare it to. You need to have the map to compare it to. Also, you can get what's called platform-induced effects. So as this quantum device is moving around, that could be causing interference with the sensor itself. So you need to have really good, so it's not just the quantum side, it's also the classical filtering side, algorithms, error correction, because you need to filter out what's noise and what's real. And so in these cases, we want to have a very good sensor for detecting the magnetic field anomalies to start with, and also the really good magnetic maps to be able to compare those sensor results to. So I love the name of this device. So this is an actual field-deployed quantum magnetometer by Lockheed Martin called Dark Ice. And this is a nitrogen vacancy center diamond-based quantum magnetometer, and it enables accurate airborne positioning via geomagnetic anomaly measurements. So again, anomaly measurements. So these sensors are incredibly accurate, very sensitive. And so now we can put one on an airplane and use it to navigate. This device has a wide dynamic range, very high bandwidth. I don't have the parameters because they didn't make that public. And very compact size, so roughly 30 centimeters in length and 15 centimeters in diameter. These prototypes demonstrate the feasibility of having field-deployed quantum magnetometers. And this isn't the only one. I can name a dozen such devices that have been field-deployed in many different industries, like mining, energy sector, things like this. However, like I said, I want to talk about the limitations of this technology as well. So a key limitation of this form of navigation is the quality and the availability of the magnetic maps that you want to compare your data to. Or if you're doing quantum gravimeters, then you have to have gravitational maps to compare the anomaly measurements to. So therefore, we really need high precise magnetic navigation. We need high precise magnetic maps in order to implement this navigation technique. And also being able to improve our modeling. So there might be roles for AI and quantum computing in improving the magnetic field modeling as well. So this issue is particularly noticeable with these NV-centered devices because they're using what's called vector navigation. So vector, so 3D, so X, Y, and Z. So we have these vector maps of the magnetic field anomalies, and that's not typically available. Usually our classical technology is creating two-dimensional maps. They don't usually have that third-dimensional depth into the Earth. And so that means to create a vector map to compare to our measurements, we have to calculate it from what's called magnitude maps via these gradient calculations. So this means that we're limited by the historical maps that are available and also the resolution of that original map. And like I said before, there are additional errors that could be introduced by the altitude of the platform, of the sensor itself, or both. So you can have platform and velocity dependent fields because you are moving, for example, a metallic object in a magnetic field. So that's going to cause its own electric magnetic fields on its own. So I think that the future will be hybrid. Rather than replacing all the existing classical sensing systems, it's better to add quantum sensors as complementary technology to your PNT network. And so most of these quantum sensors I've been describing, they rely on single sensor units or sensor ensembles where few devices are demonstrating clear quantum advantage. But just like quantum computing isn't necessarily demonstrating clear quantum advantage yet, it doesn't mean it won't A, happen in the future, and B, won't happen soon. So these techniques, as they become more feasible, as the technology matures and our engineering improves. Wonderful, wonderful. Okay, so I'm gonna stop sharing and just open up the floor
We
and
do have a
see.
question. So I think I'm just confirming, I confirmed with Nathan, we're having trouble trying to find the Q&A box. So if you need to, I'll just look carefully at the chat. Rainier does have a question here. Is the magnetic field stable enough over time to provide accurate navigation?
I mean, that's what the tests have been showing, that this is a feasible technology that we could use in, say, GPS denied environments. You could deploy a quantum magnetometer. For example, say you're a farmer and you're trying to plow your fields and harvest your crop. All of the farming equipment now runs off GPS signals. And so if you lose satellite signals, if we have a solar flare that knocks out large amounts of our technology, of our infrastructure, they can't harvest their crops now. All of that is going to be wasted. And so if they had a field deployable quantum magnetometer, for example, that they could then in emergency situations engage, now they have their positioning, now they can plow their fields. So this would be an example.
And feel free, anybody else, if you want, you can raise your hand if you prefer to just ask your questions, since we are at the Q&A part.
And I think that the Lockheed Martin also was showing that the device was accurate enough for their navigational tests. But there's not that much information online. Yeah. I think there might be another question in the chat. Oh, and there's a hand up too.
Yeah. So Deepak is saying there have been studies that say the Earth's magnetic poles are slowly shifting. How does it affect given the above question?
Yeah. As far as I understand, as poles shift, if the magnetic field flips, that could affect things for sure. There's other ways that we could still navigate with quantum sensors. So using a gravimeter instead. I don't know if our gravitational fields are shifting as well. But yeah, so again, it would be as the field is shifting, I'm guessing that the maps would have to also be updated, but I'm not necessarily an expert in that.
All right. Godwin?
Yes, good day. Dr. Kuntz, thank you for the insightful presentation.
Thank you.
My current research actually focuses on modeling communication, between, passive UHF, RFID tire sensors and RFID readers for transportation applications, just like the automotive that you were talking about, where the sensors are mounted inside like a rotating vehicle tires.
Okay.
So, with that, we can like detect if there are like issues with the tire, and then we can like give predictive measures to say, oh, like the technology we're trying to like build a dashboard that is, attached to the car that, alerts the driver to say, oh, there's an issue, and so you can fix
Mm,
it just to reduce, all these transportation issues in the US.
mm,
So, given the role quantum sensing is beginning to play in positioning, navigation, timing, and all this advanced sensing that you just mentioned, do you envision a future where quantum sensor could be integrated, with um, these RFID-based transportation monitoring networks um, and if so, what area would you consider the most promising entry point for this? Yeah, thank you.
oh, so I would say for sure, I could see quantum sensors playing a role in transportation applications. I go into that in some of my courses in my training, both with Nate and through Qubo Consulting's Q Academy. But right off the top of my head, I'm not sure about the best entry points. I'm very aware of like quantum LiDAR, accelerometers, gyroscopes, helping with that.
Mm.
But there's so many applications. So I would love to talk more with you offline about this.
Okay, 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 okay,
Yeah,
okay.
please send me an email. You can contact me through my website or it's Katanya at cuboquantum.com. Maybe one of my wonderful team members can put my email in the chat.
Okay. I actually already sent you a message on LinkedIn.
Oh, wonderful. I thought your name looks familiar. Yes, I think
Yeah,
we're
I
connected
connected
now.
on LinkedIn and yeah,
Yes, wonderful. Thank you for connecting.
yeah.
Awesome.
So, but I
Uh,
wouldn't mind
yeah.
getting the email as well.
Yes, we'll put it in the chat.
Thank you.
Yes. All right, I have one more set, quick presentation before we bring on our guest speaker, if that's okay. We're going to talk about quantum LiDAR to finish up. I don't see any other questions, so I'm going to go back to sharing my screen now. Go. Yes, okay, good. So I want to just finish up with explaining what is quantum LiDAR and quantum radar. So quantum radar and quantum LiDAR are similar to the traditional radar that you might have heard of before. So this is like with using classical traditional radar is using classical radar radio waves and microwaves to measure an object. And LiDAR is where you use visible light, like lasers and things like that, to measure an object. So that's the traditional side. So quantum LiDAR is now where we replace either the signal or the detector with something quantum. So the signal could be now entangled photons or single photons, and then the detector it could be still a classical detection, or it could be a quantum detector, like a photon number resolving detector, like we'll hear about very soon. And so quantum LiDAR is harnessing the quantum properties of these photon states, these quantum states of light, things like entanglement, coherence, superposition, to improve the measurement sensitivity and accuracy. So you can see in this is a very like high level scheme idea of how quantum LiDAR works. So one version is you have an entangled photon source. So entanglement is where you have two particles of light, two photons, and they have a special correlation. They have a special relationship. So one photon is called the signal, and the other is called idler. And you see this figure 8 here. So that's the universal sign to show that something is correlated, entangled. And so these two photons, you can send one, goes to the object, reflects off the object and comes back and is measured. And then the other photon, the idler, goes straight into this detection unit here. And so by keeping one of the photons with you, it's going to give you, for example, a very precise timing signal. because, for example, you can create photons that are entangled in time. And so their times of arrival will be correlated. There will be a special relationship that you can then derive, and you can improve signal to noise ratios by exploiting that timing signal relationship. And so by sending the signal photon to the object and then measuring it when it comes back and comparing that to the idler measurements, you can make sure that the data that you keep is the real data that you wanted, i.e. the signal photons that were reflecting off the object coming back, and not noise, not background. So you can actually remove background noise because it won't be correlated with these special entangled photons. So like I said, traditional radar is using classical electromagnetic waves, light, or radio waves, also a form of light, to detect and locate hidden objects by measuring signals that are reflected off that object. So now quantum radar is where we're in the microwave domain. So microwave radiation, just like your microwave oven. And quantum LiDAR is in the optical domain. So the light you can see with your eye, like rainbows, like, red, blue, green, those colors. So you can send entangled microwave photons or entangled optical photons towards a target and then measure that correlation between the entangled photon pair that's kept at the source, kept at the detector, and then the returning signal. Okay, so if you don't want anything technical, go grab a cup of coffee for 3 minutes. We're going to have a little quantum LiDAR, quantum rabbit hole. So what is quantum illumination? Very similar to what I just explained. So this is quantum LiDAR is like the overall umbrella name, and then quantum illumination is specifically referring to entangled photons. So when you have this signal idler pair, one photon again generated at the source, sent to the object, come back, and then the other one is here and measures, you combine it with the idler to compare. And so theoretically, we can get a much higher sensitivity and or improved signal to noise ratio using this method compared to classical light of equivalent brightness. So here's an example of a quantum LiDAR experiment with photon number resolving detection. That's what PNR stands for, photon number resolving. And so in this experiment, we're not actually using photons. So this is not technically illumination. This is quantum LiDAR, but the source is a laser, as you see in the middle here. The source is a laser, and then the quantum side is the detector. See this shiny silvery thing here, SNSPD. If you remember, I said that earlier in the webinar. So superconducting nanowire single photon detector. These devices can measure exactly how many photons are in the light pulse that it arrives, that it measures, that arrives at this detector. So if you can distinguish, was there one photon or was there two photons or three photons, if you can filter out based on photon number, you can actually improve the performance and reduce the background noise and get a better measurement. And so this quantum-inspired LiDAR has been proven to show advantages by using both the single photon detectors and the computational algorithms for filtering the data. So they use this active photon numbering filter, and this is achieving noise-free target reconstruction and imaging in daylight. So sometimes the limitations of these devices were they couldn't operate in normal environments with the sun, because you're trying to measure single photons. Those are very, very, very weak signals, and the sun is very, very bright. So it's hard to do that, right? But no, this was done in real daytime. And again, using like a classical source, a laser. A laser is considered like a semi-classical source. It's not technically a full quantum source. And so the quantum part of this is the detection. Wonderful. And so, like I said, in this demonstration, it's quantum-inspired LiDAR detection of outdoor targets. They were finding a steel pylon that was roughly 1 kilometer away, 900 meters away, and it was in the daylight. And they're using photon number resolving detection with an array of superconducting nanowire single photon detectors. They also propose a practical algorithm called an active photon number filter, and this is for processing the data that's collected by the PNR detection, which improves the overall signal-to-noise ratio. And so basically, I know we're getting a little in the weeds, but here's some pretty pictures. So this is the raw experimental data collected of the steel pylon. So in this insert here, in this figure F, in this insert, the small one, that's the actual pylon that's under study. So that image was collected using like traditional classical techniques. So we have a ground truth to compare our quantum measurements to. And then these A, B, C, D, these are the raw experimental data that's been collected when they set their resolution for just 1 photon, and then B would be 2 photons. This is 4 photons and 3 photons. So as you can see in this A, you actually get the most detail of the structure when you use the single photon regime, when you filter out everything and only look at the single photon pulses. And then they applied an algorithm to help clean up some of the noise, and then that's what this processed diagram here is. And so you can see, compared to the ground truth, you've captured all of the details that you were looking for. In case you are interested in the technical aspects, I've defined all of these little acronyms here as a little table here. And also all of my slides that you'll be getting a copy of have the publications on the slides. So in case you want more information. All right, we're going to pop back up. All right, so like I said, with quantum illumination, quantum LiDAR, there are still practical limitations we need to keep in mind. So in this case, the one significant constraint is the requirement of having prior knowledge of your target range. This is commonly referred to as the range problem. So you kind of need to know where the target is approximately located in order to deploy this type of measurement, because it's time of flight. You're working with times of correlations and things like this. And so this limitation is confining you to more of a scanning application right now. But there are ways to address this range problem that are still actively being explored. Things that include modulating the frequency pulses that are being sent towards the target, because then you can do what's called joint pulse radar. So significant challenges arise in these medium to long range radar applications when you're sending, for example, what's called Gaussian states or coherent states of light. These are the states of light created by lasers. So these are called coherent states. And so when you're using that type of light to do the measurements, you're dealing with very low signal intensities, because that's what's required to harness the sensitivity of the quantum illumination, quantum LiDAR. So there's an ideal intensity range in order to leverage the quantum advantage. You don't want to go too high, because if you go too high, if the intensity is too high, you're pushing outside of the quantum advantage. You're starting to go from quantum to classical. If there's too many photons, it's not a quantum state anymore. It's now classical state. But if you go too low in your intensity, then it might mean you can't measure the very weak returning signals. So there's a sweet spot. So I found that there's a very common theme in quantum illumination. It can provide several advantages over coherent classical illumination if you can detect the weak signals and filter out the errors. So things like post-processing, filtering, and using algorithms and AI can make a really big difference in your results. Awesome. All right. That will be concluding my presentation for today. I just want to check in to see if there's any other questions before we transition to our guest speaker. I do see some questions, so I'm going to stop sharing.
I'll come back.
All right.
We do have a question in here
Perfect.
from Rael. He's wondering, would it be possible to combine multiple quantum sensors in a single system for improving positioning, navigation, and timing PNT outputs? For example, using quantum magnetometers and gravitometers together to improve navigation data results.
Yeah.
That was a mouthful.
I know, this is a big mouthful today. How many times have I had to say anomaly? Yeah, so great question, Riel. Yes, definitely combining different quantum sensors together. In fact, because I didn't have enough time, there is an example right now in the mining sector. There's two companies, SB Quantum and Silicon Microgravity. They have combined, so SB Quantum makes the magnetometer, and then Silicon Microgravity makes the gravimeter. And so they both devices are portable and they can be put on a drone. And so they're currently doing a survey in Canada of a nickel mine where they've put both these gravitational and magnetic sensors on a drone, because if you can get all of that data, plus if you can also do traditional sensing, like with electromagnetic fields, like LiDAR, then you get the full spectrum to survey the ground and the earth for mining and energy sectors. So yes, definitely. That's a great question, and it's being done right now.
Thank you. We have Sandra, who's asking, can quantum technologies that have been developed to date that can obtain various data on unidentified aerial phenomena?
Oh, that's a great question too. So there are materials and potentially objects that could be detected using quantum LiDAR, quantum illumination, hidden object detection that we can't find with our traditional radar. So that could include UAPs. So who knows? I'm not an expert on that.
I think that's all that we have. And if there are further questions, we'll take them after our guest speaker presentation.
Okay, I think that's a great idea. So
Okay.
I'm gonna just start up some music first. All right, thank you. I'm gonna introduce our speaker, and then we'll bring him onto our virtual stage. All right. Sorry, Zoom changed my settings again. There we go. It's time for our guest speaker. We have a quantum tech founder who will be sharing about their company and their quantum application. Now let's pretend we don't know who it is and I haven't been advertising them. Welcome, Abdul. Abdul Mohamed is the co-founder and CEO of QuantaSense, a Calgary-based deep tech company developing next-generation quantum-enhanced sensing and timing technologies for the aerospace and defense applications. With expertise in superconducting circuit design, quantum optics, and advanced measurement systems, Abdul specializes in technologies that push the limits of weak signal detection and high precision synchronization across complex sensor networks. Abdul co-founded QuantaSense, where he contributed to the development of the quantum limited amplifiers and precision readout systems for quantum sensing research. Welcome, Abdul.
Thank you, everyone. Thank you for the introduction. I hope you all can hear me.
Yes. I'll turn the music down a little bit and let you share your screen, and then I'll stop
Wonderful.
the music as soon as we have that set up. Because it's nice to have a little intro. There we go.
How's that?
That's perfect. Awesome.
Wonderful.
Thank you. Please take it away.
Awesome. Yeah. Thank you, everybody, for attending the webinar, and thank you, Katanya, for having me on. Very much appreciated, and hopefully I can show you some good applications of quantum enabling technology and actual quantum sensing technology that we're developing. Okay, so I usually like to start these conversations explaining kind of why I care about this so much. Essentially, the biggest problem here, and a lot of the themes that Katanya talked about, is that what we're trying to do is detect weak signals in whatever modality that you're trying to do it. But essentially, the classical limits of our detectors today can't. So one good example is kind of the research I do. So a lot of the sensing that I do in the lab is meant to detect really, 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 really tiny signals inside a huge background radiation of noise. My entire job is every single day tweaking with little pieces of metal, electronics, and using the physics of quantum mechanics to eke out the performance required to actually detect these types of systems. What you notice suddenly is that a lot of the equipment that we have today really can't do some very exotic type of measurements that we needed. And so I started developing either quantum-enabled technologies or actual quantum sensing technologies to assist me. But as you can see, the problem isn't just mine. A lot of markets across this planet struggle with the same thing. So, for example, one of the best ones that I can think of that we work on every day is in radio astronomy. You can think of, these big antennas that you see. Either you might have visited one or you might see in documentaries. They usually, pop up, and they are these big satellites that are trying to detect super, super tiny signals from across the universe. The problem is that detection can be done, but it takes a lot of time, and it takes a lot of infrastructure to do that, and a lot of money. Right now, many radio astronomy observatories are completely oversubscribed. So that basically means they're essentially trying to do the experiments researchers want them to do, but the measurements that they do take a lot of time. And so they just can't fit them all inside of 1 year. And so they have to play this game of, all right, we'll do this one, we won't do this one. And it's one of the biggest struggles for radio astronomy. But that's all to say that, everybody who works at the very edge of these sensing applications struggles with this. And so the idea of QuantaSense and my co-founders, we really wanted to build a company that we knew could actually take these applications that we build in the lab and make them work outside of it. So our thesis here is we essentially detect ultra-weak signals with unmatched performance. And one of the examples that we are building right now is what we call QLIPA. This is essentially the best amplifier in the universe. There's a bunch of taglines there that matter to the people who want to buy this, but essentially these types of amplifiers take a really, really small signal and then make it really big on the other side. You can think of it like if you've ever strummed a guitar and you have an amp beside you. If your amp is really bad, the notes on the guitar sound terrible. If you have a really nice one and you spent a lot of money on it, those notes sound very crisp and clean. It's the exact same thing for quantum computing or radio astronomy or whatever type of sensing modality. The readout matters a lot. And so we build amplifiers that essentially add the least amount of noise allowed by quantum mechanics. We call these types of amplifiers quantum limited amplifiers, and I'll get to that later. So what's an example of using a quantum limited amplifier, or QLIPA? Katanya showed a dilution refrigerator before, and the whole idea of this entire system and its wiring and all this crazy stuff is to take a tiny little chip here, take its signals, bring it out to room temperature, and make your computer measure it. That's essentially what we want to do. Depending on your readout, this can be either really fast or really slow. What do I mean by slow? You essentially want to take a very weak signal. You want to make it bigger without distorting it. If you do distort it and you use kind of a bad amplifier, it takes time to actually make those measurements and be able to read out what you want to. A lot of quantum computing struggles with this today, and so an entire community is built around building these types of amplifiers. This is essentially what we want to do with the amplifiers that we use. But you can replace this with maybe an antenna, some sort of radar system. A lot of ground stations will do stuff like this. It really just depends on what you want to measure. We enable that measurement. So let's say QLIPA doesn't exist today. What's your next best thing? So today, a lot of systems use what we call low noise amplifiers. These are essentially the best noise performance, low noise amplification, but they are not quantum limited. They're able to operate down to 4 Kelvin. This becomes really important when you want to read things like quantum computers, but they are hot. They take a lot of power to operate. You can imagine you have your fridge and it's like putting a hot stove inside of it. You're battling cooling it down while adding so much heat by these devices. And so they don't really make sense when you want to start scaling quantum computers to many qubits. You need to start thinking low power, low noise. And so the quantum community came up with what we call quantum limited amplifiers. We call them Josephson parametric amplifiers. It's just the design of what we choose to put on our chips, but it can be done in different ways. What's nice about these guys is their quantum limited noise performance. They require very low power to operate, but they're extremely sensitive to anything around them. And so we really have to cool them down a lot. So you need those big dilution refrigerators that you saw before, and they need to be intensely shielded. So it's not easy to operate these guys. And so where QLIPA stands is kind of the balance of the two. Can we make something that can provide quantum limited performance, but still be able to be brought out of the lab and actually operated without these massive type of cooling infrastructure? And the answer is yes. So these amplifiers that we build work today. They operate, they're in our fridges, in others' fridges, and they do exactly what they're meant to. So I hope that gave you kind of a feeling of the amplifiers that we build. I wanted to give a bit of a flavor of some of the long-term work we actually plan on doing as well. Oh, sorry. I just wanted to give it a little explanation on the markets. I've kind of been hinting at it here and there, but some of the work that we do is obvious for quantum research and quantum computing, where you're trying to detect really small signals from your quantum computers. You need these types of amplifiers, and also aerospace of all things. So radio astronomy kind of sits in that aerospace regime, but you can think of deep space communication. If you're doing, if your country is doing detections all the way to moon, to the Mars, equipment that's really, really far away in our solar system, you need very, very well abilitied amplifiers to be able to detect those signals quickly compared to the state of the art today. Okay, so the next product that we kind of think about, I like to introduce by kind of giving you an example. Right now, anytime you purchase coffee, anytime you turn on electricity in your house, anytime you use GPS, there is a very well coordinated series of calculations that goes on behind the scenes to make these detections possible and make these operations possible. This is what we call GPS or GNSS, so Global Navigation Satellite Systems. But the question becomes, okay, what if one day everything goes wrong and we lose GPS, we lose GNSS? What does a country do without that? And so our long-term vision is building our own timing synchronization system that is capable of addressing an entire country. Not only that, time synchronization is super, super useful in defense or even in GPS. So you can think of, the speed of light is this huge number. And so you need very, very precise precision in the time to measure anything related to distance. And so we need these very precise type of time synchronization systems to be able to deploy these. So our long-term version is building what we call Guardian Link. This is a time synchronization system that's designed to keep systems clocked together. So if one side sends a signal and you detect it on the other side, you want to be able to know the amount of time it took between those two detections so that you can calculate the distance, velocities, and all sorts of calculations that happen in between. And again, this happens all over your life. You just don't notice it. So every time you use Google Maps, every time you want to buy a cup of coffee, these signals come into play and are kind of the backbone of all the technology that we've built globally. One of the best examples I have of GPS going wrong is Tesla. So Tesla's autopilot relies on GPS tracking to be able to keep you on the road. And GPS is great. It keeps track of where you are down to about 5 meters, so on the road. But researchers love to play these types of games of, hey, what if someone tried to build like a really crappy type of system to actually make these Tesla autopilots think, oh, the road is like 30 meters on to the left or right of you. And this actually works. So you can, what we do is what we call spoofing. You can make the Tesla autopilot think, hey, the road is actually 30 meters to the right, and have it actually swerve off the road. And this is very well documented. Researchers have done this quite a bit. I find it kind of funny that they like to do this type of stuff, but it brings in a real big question of, okay, if I can't keep these things secure, what is the next best thing? And one of the things we're building is able to address that. So because we use a special type of light, essentially, we're able to tell the difference between all sorts of light and the light that we want. We're able to know if some, well, let's call them bad person, wants to send light that isn't the one that we want to measure. And so we're able to mitigate that and immediately address it on the fly down to a few nanoseconds. Very, very quick. And so, yeah, this is one of our long-term visions and something we've been building with some partners, and we're developing not only for defense, but commercialization as well. To be honest, the technology that we usually build here usually stems from the idea of, okay, we actually need it in the lab, so what can we do to build it? And then we start thinking, oh, okay, we can actually do this outside the lab as well. Yeah, so this is kind of the two technologies we're building. I wanted to give a bit of a shout out to my team. I'm the CEO, Abdul, and the rest of my team are just as innovative and good at what they do in terms of quantum sensing. And we've worked hard. We built this company at first thinking, oh, this will be something fun we can put on our CVs, but we've really made it grow and have really matured it into something that we think has a positive benefit to the work in Canada. Yeah, we have employees that we've hired as well, doing some of the work that you saw in the previous slides. But otherwise, yeah, if there's any interest at all in any of the technologies I spoke about, feel free to reach out. I'm always happy to chat. One of the things I like to end off my conversations with people is quantum isn't something, at least quantum sensing isn't something you think about 5, 10, 15 years in the future. It really does happen now, and it works today. It's not something you have to think about as a future concept. If you want to see them working in the lab, I'd be happy to show you. And yeah, I'll leave it there. Hopefully I didn't take too much time, but if anybody has any questions, yeah, feel free to ask.
Amazing. Oh, sorry.
Yeah, no, absolutely. Thank you, Abdul, for that. That was a very informative presentation. I have Sandra here who's asking, can you go into a little more detail on the shielding materials or structures?
Yes. So the wording I chose there for those types of amplifiers is what we call a Josephson parametric amplifier. It's a special technique in generating these types of amplifiers, but because you use this Josephson technique, they become extremely sensitive to any kind of radiation outside of it. And so what we do is we actually shield it with superconducting material like aluminum, so that we essentially build a Faraday cage around it so that radiation can't pass through. What's nice about the amplifiers we build is we don't care about any of that. It's very tolerant to those types of things, and so we don't have to think about those kind of things.
Thank you. Giannis, or actually Dr. Katanya commented that she got to see the dish in Australia, and Giannis added there that he bets it costs a lot of money to maintain and run those dishes.
Yeah, so I It's about, I was doing some research we've actually been partnering with an observatory. It's about $40 to $50 million a year to keep those things going.
Yeah.
So it's not cheap.
Giannis also quipped, best in the universe. I knew a few extraterrestrials who may take offense.
Well, if they're following the same rules we are, unless they know something about quantum mechanics we don't, they should say the same thing.
Sorry to interrupt you. Abdul, would you be able to just stop sharing because then we can
Oh,
see the
yes,
whole
please.
room
I'm
on
sorry.
the gallery? No, it's all
Of
good. It's all
course.
good. Yes, please go on, Lorna.
Yeah, by all means, is there anybody else? Feel free to just raise your hand, unmute your mic, or if you want, I think Sandra just added here in the chat asking if you are collaborating with SpaceX with your research and technologies.
Currently, no. It's kind of difficult sometimes to actually get these conversations with commercial entities, especially when they're really massive. It's kind of a rabbit hole of who to talk to and who has the right ideas that can make sense of it. So, kind of our approach is build it for researchers first, then build it for small quantum computing companies who understand the problems, and then really start approaching these big commercial entities. They really start looking at you when they hear it's kind of a word of mouth game. Engineers, no matter where they are, talk to each other, and we all kind of know the space between each other.
Thank you.
I
There is a
have,
question. I know that this was during Dr. Katanya's Q&A, but maybe for both of you, Yamini asked, what skill do you see as the biggest skill gap in the coming years with quantum gaining momentum?
Could you repeat? Oh, I see it. What do you say?
So I know that question was asked directed more to Dr. Katanya, but if you have any input in that too, by all means.
I can let Dr. Katanya go first, and then maybe if I think I can add anything to that, I'd be happy to.
yeah. So that question's more about, I think, skills and education and training. And so maybe I have a different question to ask first, if we could, and then we'll go back to that one, if that's okay.
Mm-hmm.
Okay,
Of course.
cool. Yeah, so Abdul, I loved what you said at the end, where you pointed out that there's a lot of quantum sensing technologies that are commercialized now, available now. And I just love to hear more if you want to expand on that. Like, are you allowed to talk about any of the clients that you have and how they might be using your device or anything like that? I know sometimes a lot of quantum sensing companies, like you mentioned, defense, so you can't talk about it. So I respect that.
Yeah.
And you are
To
being
that
recorded.
end, I can't talk to that end, but I can give a generic feel for the type of companies that work on this. Defense is obvious for a lot of the time synchronization stuff we do. It's just the better precision and the more security you can apply. They, I don't want to sound too rude, but they kind of salivate over those kind of things. It's the things they build up on,
Oh, for sure.
and it's not just Canada. Like if you search up time synchronization, Australia, Europe, any sort of country, there's going to be 4 or 5 researchers doing the exact same thing. It's kind of the next big push that a lot of the quantum sensing community is looking towards. But researchers themselves, so at the heart of this, like whenever we try and think about building these technologies, the first question is, okay, what would my neighbor want? And so the amplifiers that we build, we put them in fridges, and they work. They do exactly what they're supposed to. Time synchronization as well. We run experiments and write papers building these types of things. But I can't name names specifically, but hopefully that gives you kind of a vision of where how we think about this stuff.
Yeah, that does. And I agree with your assessment. Timing and synchronization is a very hot topic. And just like how there's a quantum space race going on with quantum communications, there's definitely a quantum sensing and like quantum time transfer space race going on.
Yes, exactly.
Yeah. All right, back to you, Lorna.
Yeah. Sandra has another question for you, Abdul. Do the quantum technologies you described have an application in the Trump administration, quote, Golden Dome, and similarly applied to Canadian defense?
I'll be honest, I don't know the Golden Dome. the US right now is kind of a hot topic, and it's not very stable at the moment. We've seen a lot of the quantum research and quantum work that's gone on in NIST, and a lot of other organizations seem to have been affected negatively. And so my focus usually is within my local community, or as best as I can within Canada. But unfortunately, no, I don't know what the Golden Dome is. In terms of the technology itself, yeah, it's something, a very long-term vision, and it's something that's going to be very difficult to achieve. You have to convince an entire government of Canada to be like, hey, this technology works. We should implement it as a backbone strategy. It's not cheap and it's hard to do. And so, I like to think of it as baby steps. I just take it one step at a time and see how far we can go.
I agree. And building a vocabulary and awareness around what is this technology, why is it so powerful, what is its actual purposes and uses. I think that's the really important steps. And your presentation did a great job at that, so thank you.
I'm glad.
I have a question from Abdul here, or I'm sorry, for you, Abdul, from Anthony, and then Giannis has his hand up, and we'll go to him afterwards. So Anthony's question is, how does QKD integrate into the existing identity and access management architecture without disrupting MFA workflows?
Ooh, you've hit a very specific topic that I am unfortunately not an expert in. So I'll have to leave it at that. Everything I say after this is kind of a big asterisk, so it's kind of my own thoughts. But yes, QKD is something that we know works, but it has its own vulnerabilities. In terms of how it actually integrates in those type of effects, like multi-factor authentication, I'm honestly not sure. So the way QKD works today is we essentially distribute a key between the two parties, and we're able to use that key when sending messages between each other. I wonder what that would look like in multi-factor authentication. That's actually a very good question.
I think, Anthony, I should get you in touch with VeraCloud. Unfortunately, he was unable to join the webinar last time when we had VeraCloud as one of the speakers for quantum communication, and they would definitely be able to explain that. So I will get you in touch. Don't worry. I'm making a note.
Giannis, feel free to unmute your mic. We can't hear you. Okay. Time out.
Restart.
Sorry. I'm not mirroring my screens, so I'm having to shift between screens, and without a mouse, it's not easy. So thanks very much, Abdul and Katanya, for the presentations. These were really great. Apologies for the joking that I was doing earlier.
No, of course, that's totally fine.
It's just there's a bit of an anthropocentrism in there that as an environmentalist I have to question.
No, that's fine.
But I have three questions actually for you,
Okay.
if I'm allowed to, if we have the time. But this is a question. The first question that I have for you is a question that I've been asking a few of the other entrepreneurs and CEOs that we've met through the Qubo. I've been doing a lot of the Qubo Consulting videos with Katanya and Lorna, so this has been a fun ride, especially for an outsider. For me, I'm an environmental. I have a PhD that I just finished with environmental studies at Queen's University. So great to be a PhD. But that's enough about me. So yeah, my question for you is, the first question that I have for you is, do you feel that people understand what you do, or that what you're trying to do?
I would say I hope so. Obviously, like it's a learning process. And honestly, you're the best judge of that. So if there's definitely some parts of the conversation where you're like, what is he talking about? I'm always happy to hear it, always willing to have those conversations and hear those types of criticisms, because it helps me understand, okay, this didn't make sense to anyone. Let's talk about it further. It really just depends on my audience, if I want to be specific. So the audience today is a wide range of people with their own types of knowledge and experience. And so it's I can't really go into those technical details, or I try my best not to. Hopefully I manage to do that a bit better than as I do these types of presentations. But in terms of, if I'm speaking to another technical team or technical companies, it's much easier for me to just dig into the weeds and tell them all the type of specs that my devices use. Yeah, hopefully that answers your question.
It does. I mean, I guess the follow-up question I have is kind of related to that question, but also to some of the stuff that you said. So, a lot of what we've been hearing, of course, there's a civilian aspect to the technology. There's all kinds of uses that are possible, but the defense stuff comes back all the time. Do you feel that this has an impact on how people perceive you so far? Or do you feel yourself that has kind of parked you in a kind of direction for,
Yeah,
yeah.
and sometimes yes. So especially with the right audience, like when people hear defense, they think, especially with the investors or in those types of conversations where people want to see, how are you growing? Defense is one of those obvious things that says, okay, if you can get through, then you can get money. But the biggest problem with defense is it takes forever to get through. So they're very stingy. They don't like to talk too much. They don't, have these dialogues that are easy to have conversations with. But they're getting better. There's a lot of proposals out there that help with that. In terms of putting us in a box, sometimes, a lot of the quantum sensing, when you know usually the first question is, okay, does this have any help with defense? And the answer is usually yes, with an asterisk, if we can find some sort of partnership and a marriage of the technology. But when I'm actually really talking to technical founders, my number one job as a CEO is essentially bring in money. And so usually my first customers are the ones who want to try it first, who want to try something that might not be absolutely perfect, but are willing to take that chance. And so I kind of flock the herd in that direction. I'm not always, gunning for defense and wasting all my money in that direction. My first job is to get customers.
That's a great answer.
Okay, I'm glad.
No, but as CEO, I mean, that is the best answer you could give.
Yeah, no, yeah.
If your shareholders were with us, and maybe some of them are, bravo,
I
Abdul.
won't name names.
You nailed it. You nailed it.
I guess my last question, if I may, I know Monica has her hand up here, but my last question is, this is kind of another question I've been asking other CEOs out there. Is your company involved in any kind of social licensing? What are you talking to the larger public? I know there's a lot that you can't talk about, but it seems to me that there's a lot of, so if there's defense, usually there's government funding of some sort that goes on in this. And this for the research and development aspect, but also for the use aspect, transformation of these technologies into usable devices. Not saying that that's necessarily what's going on for you, but there has been that in the past in other conversations. But I'm also finding that because of this, when we talk of who the stakeholders are, oftentimes the government shows up as one of the main stakeholders, but not necessarily the people who might be, let's say, near the plants where this is manufactured. The mining that's involved has an effect on the environment in some sense. Do you feel tied to the larger kind of environment in that sense? How do you position yourself?
No, that's a good question. So, yeah, I can think of it. A lot of the work that we do to build our devices, build our chips, it does require volatile processes, volatile chemicals, those types of things. Thankfully, Canada has very stringent rules in how we operate in those kind of effects, and that there's a global understanding that if you use these types of techniques to build or destroy or do whatever you need to, that you have a way to be able to safely get rid of them. But it's a very good question. Like, how much what's the word? Environmental kind of pain does it come at the cost of building these types of technology? I think right now it's nothing terrible, and we have guidelines in place that tell us, okay, this is how you should actually dispose of these things. These are the type of tests you should do to make sure they're safe for humanity. But beyond that, I don't have really the technicals, or I've never really thought, okay, where do those gases go that I use to maybe make those products or those types of things. But I hope that the infrastructure around it have thought and have the experts that are necessary to deal with those types of things. And it looks like they do. So when I walk into, we build in what we call clean rooms. So we wear, if you've ever watched the zombie movie and they're wearing the big bunny suits, I wear the exact same thing to develop these chips. We work in clean rooms with volatile materials to develop these things. But we have very stringent ways of dealing with them and making sure it's safe on the other side.
No, that's great. Thanks for that. And it's not just in terms of the environment. It's also in terms of the social, corporate social responsibility measures that everybody kind of has to think about nowadays. And I'm just finding that as an observer, I'm not finding that the quantum mechanics companies out there have that in their radar.
Yes, and I agree. It's it kind of gives me parallels to AI sometimes, and some of the social implications on those, whether it be environmental or public. But right now, for quantum computing, or quantum in general, it isn't enough of a. You'll never hear, oh, quantum computing is taking away the electricity from this neighborhood or that neighborhood. The technologies we build are designed to be very efficient and very not energy intensive until we really start talking about scaling and stuff like that. But that's a quantum computing company's problem, not mine. For a quantum sensor, they're very lightweight and very easy to manufacture and lean on the environment and socially as well. There's no one who's going to be like, oh, Abdul's QuantaSense is destroying my neighborhood or something like that.
Well, I mean, if I may email you and continue this conversation, I might present some counter examples to that.
I'd love to hear them. It's always good to keep this stuff in the front of the mind, to be honest. And I never want the company to, become a problem globally or in the community itself. My number one, my first job as a CEO is to get money, but then I want to be able to develop a good social community of whether it be employees or partnerships that allow us to, help the future generations. One of my favorite quotes, I think it was a Greek philosopher, is that his mission was to plant the seeds so that the children could use them as shade. And that's kind of the philosophy I have as well.
Yeah. But even just in terms of public relations, it's for your company. It's not so much necessarily that your company would be negatively affecting the environment or the people, but that your company could be misperceived. There's a lot of misperception.
You're 100% right.
So it's important to think about this. But I'll probably send you an email with a bunch of questions. I'm going to stop talking now so that Monica can finally ask her question. my apologies.
No,
thanks so much.
Thank you, Yanis.
Yanis, we always love your mind-stretching questions. It's always fun to have you in the room. Hey.
Yeah.
It's something when we know you by name.
Yeah. It's Dr. Yanis now.
Dr. Yanis, congratulations.
That might not be a good thing for the rest of humanity. I might have to start doing public relations and corporate social responsibility stuff just for me, for being an annoyance.
We'll ask Abdul after he gets those questions from you.
Sorry, Monica, what was that?
Yes, I'm saying the still dopamine is high. Yes, another doctor, but in economics, myself. So, well, I need to say that, yes, very elaborative questions. Actually, I lost the track at some point because I really had some uh, only short issue because I am not physicist, so I can't really get into these subjects. But Abdul, I just would like to know just briefly how you see, because when you're dealing with all these signals and you have the exposure on the space and everything really is like the pollution of the signals. How do you need to kind of enhance your methodology or your method to kind of be more kind of effective, facing that, you know, is kind of plenty of signals that they are like not doing anything there, but they are just kind of contaminate the space, yeah?
Yeah, it's a very good question. Like one of the best examples is the amplifier. It doesn't matter what signal goes through it; it has to be amplified. There is no choice. No matter what signal goes through, that's what you get on the other side. And so the pollution side of things, thankfully, I don't have to deal with it. My job is to really just integrate my amplifiers and let the process happen. So, for example, you know, in radio astronomy, they do get lots and lots of pollution, whether it be from the sky, horizons, or just planes passing by, sending emitting signals back and forth. This is always a problem for them, but they have ways to mitigate it. And so my job is really just build the best that I can and then use your infrastructure to deal with it as you need. In terms of the time synchronization, yes, that's also a good question. So luckily with the systems we build, we try our best to think forward and think, okay, if it worked in the lab, it doesn't mean it works in outside of it, right? You have to think, okay, what's out there that could destroy everything I've worked so hard to build? So we think about those things, light pollution. Is there any type of radiation that gets in the way? Temperature variations, magnetic field variations, are those things that are terrible? And one of my favorite things that I like to do is when I'm building these products, we try our best to kind of break them sometimes, and we'll put things in the way of them to try and simulate as best we can what happens outside. But at the end of the day, your job is to build it, bring it out of the lab, and then have someone test it. If it fails there, you know, that's kind of the thesis as well as for a quantum company. You have to decide, like, okay, is this actually worth pursuing further than that? You shouldn't die on products that just don't work.
Yeah, obviously. Commercial side of the story.
Yep. Yep.
Thank you. Okay.
No worries.
Wonderful. Thank you very much, Abdul.
Of course.
We're starting to lose a few people as we get closer to another top of the hour. So maybe if there's more, I think there might be one more question for you in the chat from Sandra. But maybe, did we ask the one from Anthony? I'm not sure. There's one above also. If we... Oh, Lorna, you're muted if you're talking.
Yes, also with Anthony. Anthony, his question, what are the top of mind correlations and concern areas between the presented quantum tech and drone surveillance tech, as the latter is becoming a serious game changer in defense?
It's one of the big questions. I'm not sure how much quantum will play a role. So I always have to put my researcher hat on and think, okay, does this actually work if we want to detect drones or something like that? My expertise does not really deal with those kinds of things, but I do know that things like quantum LiDAR have capabilities of looking at drone surveillance and being able to tell. One of the hardest things to do with drones is being able to tell the difference between an actual drone or a bird or some other kind of thing in the air. How do you know the difference between all of these, especially when the environment is very cluttered and difficult to measure? And so there are techniques out there that researchers use to develop these types of things. But I have not heard as of yet techniques that I would think, yeah, that's the one that might work for now. Obviously, you know, I'm just one person with one brain, and there's only so much you can learn.
Thank you. Sandra's asking, without disclosing the companies, do you have any projects proceeding towards or currently in the pilot phase?
Yeah, so we have a pilot program right now with testing our amplifiers for radio astronomy. We're doing just that. So we build these amplifiers, we send it to them, they test it, and they say, yes, no, these are the things you need to change. And that's usually the way deep tech goes. You really want someone who can tell you with absolute honesty, especially when there's money on the table, that, hey, this works, hey, don't waste your time.
Thank you. I don't think there's any more questions. Giannis commented the Chinese have been caught developing bird-like drones.
Yeah, that makes sense.
Yeah.
I've seen also the very fast moving wings as well to mitigate being detected by different types of drone surveillance. Yeah, it's a crazy world out there, unfortunately, and everybody's trying to figure out ways to get one over on the other.
Yeah.
Yeah, literally.
Yeah.
All right. Yeah, Anthony has a question. I think Dr. Katanya, you've seen this.
Yes, we'll get to that. I want to just thank our speaker and do a couple things, and then I'll do a bonus and show about the double slit experiment. Yeah, that's I know what Anthony's talking about, so I'll give context to that question in just a second. Awesome. So thank you so much, Abdul, and also to all the attendees who have been asking questions and engaging with us. I love it. We love it. This has been great. I'm going to share my screen again. 1 second. All right. So I will show this to you in just a second. That's a little teaser. Okay, cool. All right, so yes, thank you again for participating, for joining us today. Because you've joined live, you will get a copy of our presentations. Also, this wonderful certificate of attendance, which is I think it looks pretty cool. Please connect with me on LinkedIn if you're not already. I'd love to expand and with my network and can interact with you. And now maybe you're wondering, what do I do now? You got me all excited about quantum, but I don't know what to do now. So how do I get started? Well, I really feel having a common language and a vocabulary that you understand. What is this technology? What are the use cases? Whether you're a non-technical or a technical audience, I really feel like starting out with some education is the first step. So whether it's free webinars like what we're offering, or if you'd like to check out our Q Academy page, this is on the Qubo's website. I'm also have a partnership with the Northern Alberta Institute of Technology, NATE. I'm offering 2 quantum certificate programs, Quantum for Executives, which is a non-technical 4-course series, 1 hour each course. And then Quantum for Engineers, which are 2-hour courses, again, 4 courses. So the next cohort is starting in September, and all of the registration is open on the NATE website. So if you'd like to look at the certificates, please check that out. And I'm so excited to announce we have another webinar planned. So this will be on quantum materials, the foundations of quantum technologies. It will be happening on July 23rd, same time as what we've been doing lately, this 9 a.m. Mountain. Registration will be open soon. It'll be on our website. I'll also do social posts about this, so you'll get the announcements, and I'll send an email with the link if you've been registered to this webinar. And so this will be a non-technical webinar introducing quantum materials, building blocks of quantum tech, like quantum sensors and quantum computers. We'll have a guest speaker, one of the founders of Applied Quantum Materials, a company located in Edmonton, Alberta, Canada. He'll be sharing about their silicon quantum dots and nano materials. And so this company's materials have actually been integrated into quantum computing, silicon photonics, quantum sensing, nanolithography. It's been a mouthful today, hey? Lots of words. And life sciences applications. So if you'd like to learn more, please come check out the webinar. We will record it just like this one, post it online on YouTube afterwards. So yeah, thank you so much. So now let's have a little bonus. Bonus time. All right. If you have 3 more minutes, I'm going to explain this demo. So one of the participants today so I created a quantum demo for the city of Calgary to give you context. And so this is some pictures of this laser demo. And so the image I showed at the start of the webinar is not actually this demonstration. It was a different experiment. So in this laser demo, I'm doing what's called Young's double slit experiment. So you see how there's light, these 2 light beams. So there's a little tiny apparatus in this device, and it has 2 slits, 2 holes. And so when the light passes straight through, as you see in this one here, for example, maybe it's easier to see, you see 2 lines. And so if there's no observer, if there's nothing interfering with the measurement, with the beam, we see these interference lines. We see this interference here. But if you put something into the beam that tells you which way did the light go, did it go through the left slit or did it go through the right slit? As soon as you create what's called which way information, or having an observer in the beam, all of a sudden the interference goes away, as you see in this picture here. There's no more lines. There's no more bright, dark, bright, dark, bright, dark. And so this experiment is showing very tangibly, because you can literally move something into the light laser beam and then take it out again. You can clearly see that an observer is affecting the reality, the state, the system, the measurement. And so in the classical world, this is just craziness. In classical physics, I throw the ball is thrown, there's no like ifs, ands, buts, the ball didn't go behind me, the ball didn't go side, it goes the way I thought, right? In quantum physics, we have all these like probabilities, and there's randomness, and there's superposition. And so if there's an observer, now this observer could affect the superposition of something. So like when we have a qubit's in a superposition state of 0 and 1 until it's measured. The observer is like the measurement, and then it collapses it to just being a 0 or just being a 1. And so in this case, we're in a superposition state. Did the light go through the left slit or the right slit? I don't know. So we're going to get interference. But then I put a device into the beam that tells us it went through the right slit or it went through the left one. And now the interference goes away. So that was this hands-on laser demo that I created, and is also living at the Wave Tech Center at the City of Calgary. How was that, Anthony? You can put it in the chat, don't worry about it. All right, cool. So I'm gonna stop sharing now. There we go. So thank you again to everyone for attending. I'm going to stop the recording, and we can open the floor. If anyone has more questions that they'd like to ask offline, we can hang on for maybe another 10 minutes or so. So I'm just going to stop the recording, and thank you again for attending.